Okay, so let's go ahead and begin today. I'm glad to see not everybody went home. I did get some emails, mainly, I think it was from my CP 133 class. So I think it was mainly, like first years. I guess a lot of them went home, so. But all right, so today's class, we're actually gonna go back to software. Okay, last class, you built the first hardware component of the Otter, the program counter. And if I remember correctly, that's due tomorrow. So, after the lecture will probably run about an hour or so. Um, but after the lecture, that's what you should work on if you haven't finished that yet. And then after the lecture, you'll be able to do the next software assignment, the second software assignment, which involves branch instructions. Okay, and that's what the lecture today is going to be about, where using branch instructions, that's how you can do if statements and case statements in assembly. So there's just a few things that I want to review from, actually, just a couple of things I want to review from 133, and then we'll start into material for this class. And one of the things we're going to start talking about that has to do with this class that turns out to be really important is looking for patterns in bits. Okay. There's a couple of examples after I go over the review items in 133 where we're kind of looking at patterns in bits. And looking for patterns in bits, it becomes more important later on in the course, because later on in the course, eventually you're going to get to the control units, building the control units that are part of the Otter. There's a control unit FSM, and there's a control unit decoder. And you're going to see that those control units, the coding is all based on the instructions. And you've started to learn that each instruction is 32 bits. And you're also starting to learn that bits mean certain things, like the last 7 bits is something called an opcode. And, there's other bits that are 5 bits that are addresses to registers that are within the reg file. And then there's other bits that are immediates, right? They're just numbers, right? They're bits that represent numbers. Well, you're going to see when you get to those control units, being able to recognize patterns of bits within the machine instructions can make your life so much easier when you go to model those modules in Verilog. Okay, because if you try to brute force it and basically just take instructions as they are and try to write the code based on every single instruction without looking for patterns, you can get it to work, but it's a lot more work than if you can identify patterns. So anyway, we're going to just start a little into that this week, okay, or today. All right, and then like I said, we're going to learn about branch instructions, and I got some examples up here. Also, the assignment, just like the first software assignment, where when you look in the lab manual, there's like 2 problems for each assignment. But just like last time, how I did one of them in class and then you did the other one, same thing here. I'll do one in class and then you'll do the other one. And I think that's due this Friday. Okay. All right, but let's just start with a little review, a couple things from CP 133. Does anybody remember from 133 how we can multiply a binary number by a whole number power of 2? How we can do that easily?
Shifting, right?
Shifting, yeah. How? You're right. It involves shifting the bits. Yep. Yeah, left shifting. And let's say we have, just as an example, let's say we have a binary 12, right? 1100 binary 12. So if I want to multiply that by 2, I would shift to the left. How many places? If I want to multiply by 2. This is a binary 12. Let's say I want to multiply this by 2. What would you do? You shift left, 1, and then what do you have to put in the place of get 0? Right. So you shift left 1 place, and then you bring in a 0, right? So here, 1, 2, 4, this is a binary 12, right? Because I have a 4 and an 8, but after I do the one shift to the left and bring in a 0, now I have an 8 and a 16, right? So that's 24. So, what if you want to multiply by 4? Just shift twice and bring in zeros, right? So every shift is a multiply by 2. Okay, so does everybody remember that? That was covered. I know I covered it in my class, and I think the other 133 instructors cover it. Okay. Okay, well, if you multiply or to multiply a binary number by a whole number power 2, if you shift left and bring in zeros, what do you suppose you do if you want to divide by a whole number power of 2? Yeah, you just shift the other direction and bring in zeros. Right, so again, if you started with the binary 12, right, you just shift the left direction, right, that would make it a 6, right, as long as we bring in a 0 into the most significant bit, right? Right, when you're shifting to the left to get the multiply by 2, you're bringing in the zeros into the least significant bit. When you're dividing, right, you're shifting right, you're bringing the 0 bits into the most significant bit, right? Okay. All right, so everybody, does that jog everybody's memory? Okay, so that was from CP 133, and you'll see that in today's class, at least for the software problem that I'll do, this comes into play. Now, for the software problem you have to do today, these two things will come into play, and this is where we start to, look for patterns of bits. Okay, so the first one is by looking at bits of binary numbers, right? So you had a string of binary numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, going on and on and on. How could you easily determine whether a binary number was even?
The most significant bit is 1.
When it's 1?
1 or 0.
Yeah. Let's write out some binary numbers. Say 4-bit. There's 0, there's 1, there's 2, 3, 4, 5.
Whatever it's 0.
Yeah, so if you look at all the evens, right, 0, 2, 4, and if we kept going, that you can see that even numbers have the least significant bit equal to 0, and therefore odd, the least significant bit is 1. Okay, so, that's an example of like looking for patterns. Okay. All right, how about this one? This one might be a little bit more to think about. And that's how could we determine, again, by looking at bits, how could we determine if a binary number is divisible by 4?
The 2 least significant.
Very good. Wow. Yeah, I have to write it down, but you can do it in your, right? But it's the same sort of thing. If you kept writing bits, like here we got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now just look at the binary numbers that are divisible by 4. Right? So like if you look at 0, you look at 4, you look at 8, you look at 12, just like Avery pointed out, you'll notice that for those, the least 2 significant bits are 0. And if you kept going, you would see that that's true for any binary number that's divisible by 4. The last 2 bits, the 2 least significant bits are going to be 0. Okay, so like I said, these 2 items up here from 133, that's going to come into play when we do the software assignment in class. And then these 2, being able to easily identify an odd or an even from the least significant bit, and also being able to easily identify when you have a binary number divisible by 4, that's going to be valuable for the software assignment that you have that's going to be due Friday. Software assignment, okay? But I also just want you generally to keep in mind that you're always kind of curious in this class, especially like I said, when we get to the control unit later on in the quarter, of looking for patterns of bits. Okay? All right, so the next thing. Well, any questions on anything thus far? All good? Okay, next thing is. Okay, there's this phrase here that you'll hear a lot in digital, and that's bit masking. Okay, so we're gonna talk about what bit masking is. And I mean, simply put in words, bit masking is when you want to keep desired bits while setting all other bits to zero. Okay, you'll see that there's times that you might have a 32-bit piece of data, but you only care about 2 of those 32 bits. You know, for whatever reason, like 30 of those 32 bits don't mean anything for whatever you're trying to accomplish, and only 2 matter. Or you could have a case where, you know, 30 of the 32 matter, right? And 2 don't matter. But anyway, when there's a situation where, you know, there's just a certain number of bits that you're interested in and all the other bits can be zeroed, you can do what's called bit masking, okay? And bit masking has to do with the AND function. So, I put up here, as you can see, an AND gate with its truth table, right? Remember, an AND gate, you only get a 1 out when all the inputs are 1, right? Otherwise, you get a 0 out. Okay. Well, let's say we use the variable x to represent a bit. So a bit can either be 0 or 1. Okay, so x is just representing either a 0 or 1. Well, if I take x, right, if I take a bit and I AND it with 0, I'm gonna get what? 0, right? Because from the truth table, if one input to an AND gate is a 0, it doesn't matter whether the other bit is 0 or 1, you're gonna get 0 out. Right? Okay, well now if I take a bit, right, again, it can either be 0 or 1, and I AND it with a 1, I'm gonna get what? You'll get x, right? Because if you take a bit and you AND it with 1, you'll get whatever that bit is. Right? Because if one bit or one input to an AND gate is a 1, the other bit determines what the result is, right? So this would just be x. All right, so see, bit masking is based on this. It's based on an AND gate. If I take any bit and I AND it with a 0, it's gonna make that bit 0 no matter what it is. And if I take a bit and I AND it with 1, I'm gonna get what the bit is. Right? So knowing what we want to do with bit masking, right, is, you know, we've got a bunch of bits, let's say, and we're only interested in a few of those bits. Well, the bits we're interested in will AND with a 1. The bits we're not interested in will AND with a 0, right? Because that will just make it 0. That make sense? So let's say, as an example, let's say I have 32 bits, right? Because as we've talked about in this class, we have a lot of data that's 32 bits, right? We have registers that hold 32 bits, right? So the data is 32 bits. We have addresses that are 32 bits, right? That's why on that diagram, again, you see a lot of /32s, right? We get a lot of 32-bit data. Well, I don't feel like writing out 32 zeros and ones, so I'm going to write those bits as text, right? So let's say, and I got this question last time from a couple of people, because maybe in your CP133, you didn't see this notation, but if you see 0x and it's usually a small x like that, that just means what follows is hexadecimal, okay? So let's just say we've got some general hexadecimal number. So here I'm using x to represent any hex character. Okay, up here I was using it to represent either a 0, 1. Here that x equals a hex character. Okay, just so you don't get it. Because like I said, I didn't want to write out 32 zeros and ones. Okay. Well, what would I AND this with? Actually, let me put this over here. Okay, so x here equals a hex character. Okay, well, what would I AND this with? Okay, we got this 32-bit piece of data, right? Again, I'm representing with 8 hex characters. What would I want to end this with if I'm only interested in the last two, the two most least significant bits of these 32 bits? So out of the 32 bits, I'm not interested in the most significant 30. I'm only interested in the least significant 2.
3.
Right, just all zeros and 3, right? So if I end this with hex 0, 0, 0, 0, 0, 0, 0, 3. Does everybody agree? I'll just get the last 2 bits of this 32-bit data, right? Because this 0 is gonna cancel out the first 4 bits. And then this is gonna cancel out another 4 bits, right? Another 4 bits, another 4 bits, another 4 bits, another 4 bits, another 4 bits. This is gonna cancel out 2 of those 4 bits and just leave the last 2 bits. Does everybody agree? See, that's bit masking, right? That I can, just by anding this 32-bit data, whether it's represented as binary with hex, I can select out only the bits I'm interested in by putting the ones where those bits are. Does that make sense? And you're gonna see that for the software assignment, your second software assignment, you're gonna have to do something with this.
If you wanted like bits 1 and bit 4, would you have to AND it with a binary number?
Okay, so let's say, look in here, so this 3 here represents 0 first, second, third, so it would be a 0, 0, 1, 1, then I'm ANDing this, right? So that's why I only get the last 2 bits here. So you wanna, which bits do you wanna keep? You don't, instead of keeping the 0th in the first bit, you wanna keep what bit?
Oh, okay, understand. I was saying the 3rd and the 0. But you just-
Okay, but let's do it, because other people, I think this is good for other people too. So you wanna keep the 1st and 3rd, did you say?
Yeah.
Okay, so if we wanted to keep those 2, what would I do instead of 3? A, right? You do the A character, right? Because 1, 0, 1, 0, that's 10, which is A and half. That make sense? Okay,
So it's important that our equivalent binary bits line up with the bits we wanted.
exactly. Yeah, you want the ones to line up with whatever bits you want out of this. You want everything else to be 0 because you just want to make all those other bits 0. Okay. All right, so any questions about bit masking? All right, so that brings us to branch instructions, and that's what the main focus of today's class is. And like I mentioned at the very beginning, branch instructions in assembly, this is what you use in order to do like an if statement or a case statement in assembly language. So the first thing is check your phone. Get my computer warmed up here. So if you look in the assembler manual, and again, I made a hard copy just because I don't like looking at a computer screen, but as you should be aware by now, the assembler manual is also on Canvas. And it's really something to start looking through, seeing what instructions there are. I mean, by the end of the quarter, a lot of it you're gonna have like ingrained in your brain. But one of the things I wanted to show you from the assembler manual that has to do with today's class is that on this page here, in this table, it kind of gives a brief listing of the commands. Now, remember, every instruction has a detailed description, right? So whenever you have a question about what some assembly instruction is, that's the first place you go, okay? And if you look at this brief listing of instructions, you'll see that there's quite a few branch instructions. The branch instructions are all the ones that start with B. Right? So if you look at these, you'll see some of them have RS1 with RS2 and IMM. So what does IMM stand for? Yeah, what's an immediate in this class? Just a note. RS1, what's that? Okay, and where is it? What module on the Otter diagram is our RS1 and our RS2? Reg file, right? Yeah, remember the reg file? That's the one that has the 32 registers, right? X0 through X31. I think I told you last week, only use registers X5 through X31. Don't use X0 through X4. However, today you'll see you're allowed to use X0. Okay, and we'll talk about that coming up. Now, it's not on any of these, or none of these branch instructions have an RD, but if you saw RD in one of the instructions like you have previously, what does RD stand for? Destination register, and where is that? What module? What Otter in the diagram, you know, the module? The source registers are in the reg file. Where's the destination register? What's that? Nope, it's also in the reg file. Okay, because all your operations, right, whether you're anding or ORing or adding or whatever you're doing, all operations happen in the reg file. Okay, so anytime you see RS1, RS2, those source registers, they're in the reg file. Anytime you see RD in an instruction, destination register, reg file. Okay. In the memory module, that's where you have the program, right? Because that's the code segment. That's where you have data, which we haven't really dealt with yet. That's where you have the stack, which we haven't dealt with and won't for a while. And then you also have the memory map IO, okay, which that's where your switch data, your and also your where you're going to write to, like your LEDs and 7-segment and things like that. That's what it is. Okay. So if you go ahead and you count how many branch instructions there are, there's over a dozen. I guess there's 16. Yeah, 6, 12, there's 16. But of these 16, only 6 are what are called real instructions. Okay, it's hard to see here because the resolution is not the greatest, but in this listing, any instruction that's shaded is a pseudo command. And any instruction that's not shaded, that's a real instruction. And I mentioned this briefly during our first meeting, that there are real and pseudo. Does anybody remember the difference? I kind of just mentioned it, so it would really impress me if you did.
Pseudo is made up of.
Exactly, yeah. Pseudo instructions are made up of real instructions. And the key part of this, and you'll see why it's key, especially as we move along this quarter, is that the Otter only executes real instructions. Okay, so if you design your Otter so it can execute every real instruction, well, then it can do every pseudo instruction because pseudo instructions are made out of real instructions. Okay, so even though, you know, if you look through that assembler manual, there's probably about 60 total instructions. Only about half, I think a little more than half, are real. I think like 36 or so. Okay. So even though there's 16 branch instructions, only 6 are real of the 16. And the other thing about these 6 real branch instructions is that they're in pairs. Okay, the pairs being that you have BEQ, which stands for branch if equal, BNE, which is branch if not equal, right? So they're a pair. And then you have BLT, a delicious sandwich here, but branch if less than. Then you also have BLTU. What do you suppose the difference between BLT and BLTU is? Yeah, exactly. That BLTU, it's going to treat the numbers that are in the registers that's unsigned. If you don't see a U, it's going to treat them as signed. And then you have BGE branch of greater than or equal, and BGE. So at this time, knowing that only 6 of the 16 branch instructions are real. Probably doesn't mean a whole lot, but you'll see eventually the significance of that. Okay, you'll see that in a couple of classes. Okay. All right, so any questions up to this point? I'm gonna move the camera. Because we're at the point where we can start doing some examples now, but does anyone have any questions? At this time? Might have to move the camera twice. All right. When I get over here, somebody could remind me to move the camera. All right, so yeah, I just have several examples up here just to give you some, some examples of what the code looks like for these if statements and also a case statement. These two here would be like a if state examples of if statement, and this would be an example of a case statement in assembly. So just like for the first software assignment, and the same is true for the second software assignment, all software assignments, make sure you show a flow chart. So here in this example, we have this flow chart here. And as I mentioned in the first class, but it's the first time you've seen it in one of my examples, when you have a decision point, okay, a point in your flow chart where, you would branch, either two directions based on what the result is, you show it as a diamond shape. I should have made it clearer, but these are diamond shapes, okay, these decision points. So here, we're just comparing the contents of two registers. You can see X5 and X6. Again, where are those registers located? Where in the diagram for the otter? Right, they're in the reg file. So we're talking about, contents, data that's in that reg file. So you see, we're making a comparison, seeing whether the contents of register 5 is less than the contents of register 6. If that's true, we're gonna do some stuff over here. If that's false, we're gonna do other stuff, and then we all come together and, in a bigger program, you'd have more of a flow chart. Okay? But just for what you see here, mainly just focusing on the decision point, what we could do in this case is use a branch less than. The assumption would be that we're treating the contents of these registers as signed, right? Since I'm not using BLTU and I'm using BLT. Okay, if these were unsigned, then I would use BLTU. Okay. But then if you go to your instruction manual and you look at the instruction, you'll see that BLT is followed by source registers, right? So I'd have to put, X5 and then comma X6. Right, so it's gonna see whether the contents of register 5 is less than the contents of register 6. And if that's so, okay, we're gonna put, here goes a label. Now, when you look at the instruction, it's not gonna say label, like in the instruction part, it will talk about the label in the description, I believe. But what it will have here, it will have IMM for immediate. Now, you've already run into this in the, it was the first hardware assignment when you were doing the programming of the program. And there was that JAL instruction. And a lot of you found out that if you inputted a number, right, you inputted the immediate to the JAL, that RARS gave you an error. And you had to have it as a label instead of a number. Same is true with branch instructions. Okay, in RARS, it won't accept the number here. Okay, you have to put a label. Now, I'll talk more about this coming up. Okay, the reason behind it and why you would want to use a label anyway. Okay, but just know that when you look at the instruction, you're going to see IMM here. But when you're putting your program in RARS, you don't put a number here, you just use a label. Okay, so if this is true, if the contents of register 5 is less than the contents of register 6, well, we're going to go to where the true label is. If you put the label, then you put colon, and then, you know, that's going to be whatever this code is. Okay, now, if this isn't true, we're just going to go to the next instruction that's in line. Right, so we're going to have some code here if it's false. Right, so if this is true, it's going to jump here to this code. If this is false, it's just going to go to the next line. Now, a good practice, although this is not required, a good practice is to put a label here for whatever code's going to be done if this isn't true. And that's just for readability. Okay, so even though this false label is optional, it's highly recommended, and I would, if I was the grader, I would take off points for readability if that wasn't put there.
So the labels give the reader, information, the assembler is not actually doing anything with it.
We're gonna get to that. The assembler does do something with it. We're gonna get to it, yeah. But even if RARS didn't require a label, you would want to put one anyway for readability. And there's another reason I'll get to that gets more to what you asked in just a little bit. Okay, but there's another question. I'll come to your question next.
So in this example, after the false code runs, would it go to the true code still, or would it skip over it?
Right, that's the next thing I was gonna bring up. So I'll take care of that in just a second. Let me answer this.
Does false and true need to be all?
That's a good question. I'm not sure if RARS is case sensitive or not. But again, for readability, if you use capital here, I would use capital. Yeah, and if you use lowercase, I'm not sure. I've never mixed. Has anyone run into that? Have you done like a different case for a label and has it taken it? I just never tried it, so I'm not sure. But for anyway, readability, it's better to put everything caps or everything small. Okay, but getting to Avery's question, you're exactly right that we need to do something right here. Otherwise, after it runs the false code, it would go right into the true code, which we don't want, right, based on our flow chart. So what we would do is we would just use right here a jump command. And again, if you look at the jump command, you'll see that this here can be a label. And then you would just jump to all right, so like Avery pointed out, if this condition here is false, we're going to do this code, and then we want to jump over the true. If it is true, well, we'll jump over the false code, right? We'll go to this, run the true code, and then once we get to the end, we just want to stay there. And the way that you stay there is you just keep jumping to the same line. Oops. We use backslashes, but that's a comment in Verilog. Comment in RARS is, I think is it 2 number signs or 1 number sign? I think it's 1 number sign. It's just 1, thank you. But this is called a trap. Okay, when you just keep going to the same line, that's how we typically end assembly programs. It's just with a trap.
Is J a command or are you just saying like J as in one of the general jump commands?
Yeah, hit the command, yeah, again, you would just go. Just to verify, because. JKL. Basically in alphabetical order. Yeah, done. Yeah, just so you know, I'm not making up the instructions. So right here, see J, unconditional branch. Okay. So that's the structure, basically, of an if statement. Any questions on this here? Everybody's good? Okay, well, the next one also, is an if, but the only difference is instead of comparing contents of registers like we did here, this is comparing the contents of a register to a number, okay, to an immediate. Okay, so that's the only thing that's really different here. So let me show you how we can do this. Let me find my notes. Oh, underneath my instruction manual. Here we go. All right, so for this example here, see, the first thing we would need to do is we would have to put this number, this immediate, that we want to compare the contents of register 5 to, we would have to put that somewhere. And namely, we'd have to put it into a register. Okay, so, this is where you got to look through your instructions and you would find that there's nothing really to put. Well, there's a couple of different ways we could do it, but one way to do it, and the main reason I chose this way, which is just to introduce register 0, is we could use the add I, okay, the addition with immediate instruction. Okay, so add I. And add I, if you look at the format of the instruction, it's RD. What does RD stand for? Destination register. Where is it located? Reg file. Then there's RS1. RS1 is what? Where is it located? Reg file. And then IMM, be the number. So I chose to make the destination register. I chose to make it register 6. Now it could be any register from 5 to 31. Okay, I just chose 6. But then for the source register, what I did is I took that special register, register 0, and then I put the immediate of 10. So what this instruction is going to do is it's going to take 10, add it to the contents of register 0, and then put the result in register 6. Now, X0, that's a special register. Okay, it's called the 0 register. And the reason why it's called the 0 register is because that register is hardwired to have all zeros. In fact, next class, okay, Thursday, our next class, you're going to build the next piece of hardware, the reg file. And when you model that reg file in the Verilog code, you have to make sure that that register 0 is hardwired to 0. We want it to always have the contents 0. Okay, so that's why we can use it here, because we can just take whatever number we want for the comparison, add it to the contents of register 0, which is always 0. We'll just get that number and have it in a register. Okay. Now, some might argue, well, why not just use a load immediate? Remember, we had that load immediate command that we used to put the address of the switches into a register. Well, you could do that, but if you look, the load immediate command is a pseudo command. Okay, so you could actually say, because the add I is a real instruction. Okay, so you can save instructions. All right, so that just puts 10 into register 6. Now we can compare register 5 to register 6 with a branch if equal instruction. So it's just gonna compare the contents of the two registers. And if it's equal, we wanted to do something, again, we use a label. So we have to, jump down to wherever that code is. It's just gonna be some code. And then just like before, if it's false, that code would go right after the branch command. And then we'd have to jump to end. And end it with a trap. Okay, so I'll get you a picture this thing. So, like I said, the only real difference between these two is this one, right away, we're comparing contents of registers. Here, I just wanted to show you, essentially the additional add-I where if you wanted to compare the contents of a register to a number, you have to put that number in a register first. Okay, you had a question?
No, I just wanted to clarify, the labels are case sensitive, I just tried it.
Oh, thank you. All right, thank you for doing that. Yeah, so everybody hear that? That labels are case sensitive, so. Okay, good. Thank you so much. Okay, so before we get to this last example, and this last example would be a case statement in assembly. Let me just talk a little bit more about these labels and the immediate. Okay, so if we didn't want to use a label, okay, so let's say we want to put the number here, the immediate. Well, the way we would have to figure it out is we would have to see, well, how many instructions away is where I want to go to, right? See, in this case, I want to go from this instruction to this instruction. And let's say that this sum code here, let's say this sum code was made up of 3 instructions. Okay, so we have this instruction where the label is, then we have 3 instructions, we have this instruction, that's 4 instructions, then we have where the label is. That would be like the 5th instruction, right? Well, the way the branch commands and the jump commands work, and we're gonna get to more detail of exactly what's happening in the hardware. But the way they work is they take that immediate and they use it as an offset to the program counter. Right now, you just designed the program counter, right? In fact, that's due tomorrow. What is the purpose of the program counter? Like, what comes out of the program counter? The address of the instruction to be executed. And we talked also about how instructions are separated in address. Right? That your first instruction is always at address 0. Then where's the next instruction? 4. Then where's the next one? 8. The next one? 12. All the instructions are separated by 4 in address, right? Because they're words. Okay? So the way you figure out this immediate number, whether it's a jump or whether it's a branch, is you have to count, well, how many instructions are there between here and the label, right? So in this example here, we got 3 instructions, 4 instructions, so it'd be at this 5th instruction. Well, that means my offset would be 20 in hex, right? So 20 in hex would be 0x14. All right, and it'd be positive because I'm branching down, right? I'm branching further into the program. If I had a label that was prior, then it would be a minus number. Okay, so you see, the way this immediate is figured out is you have to see how many instructions away the label is, and it's times 4.
Is that telling you where to jump?
Yeah, exactly. It's telling, because again, what's coming out of the program counter is the address of the instruction to be executed, right? So if I offset that program counter, I'm changing the address of the instruction that's going to be executed. So, that's how you go out of order in your program, because if you're not branching or if you're not jumping, it's just going to increment by 4. Okay, and that's what that mux is. Remember the mux at the left side of the program counter? It's got like those 5 different inputs coming in. One of them's the PC plus 4, right? And that's the one you're gonna choose when you just wanna go to the next instruction, right? You're not jumping, you're not branching. But if you're jumping or branching, it's gonna choose one of the other inputs. Remember there was the other input, JAL, there was branch, and that's all being controlled by the select input, which is the PC source, which goes to the decoder, the control unit decoder. See, eventually you're gonna have to program all that. Okay, but that's a long way off yet, okay? So anyway, that's how you figure out that immediate number, is you just have to count how many instructions forward or how many instructions back, right? If it's forward, it's a positive number, if it's back, it's a negative number, and then you just go multiply by 4, right? Because instructions are separated by 4, okay? Well, like we said, RARS does not accept a number here. You have to put a label, okay? Otherwise you get an error. But the thing is, even if RARS did accept a number, you wouldn't want to do that anyway. One reason you wouldn't want to do it is because by using labels, it's more readable, okay? The other reason you wouldn't want to do it is because let's say you've got a huge assembly language program that you're working on, and you're constantly modifying things. You're adding instructions, deleting instructions. Well, every time you add or delete, you'd have to go back and figure out all those numbers again. If you use a label, RARS does it for you. The assembler does it for you. It figures out what that immediate has to be based on the label positions. All right, yeah, so that goes back to what you asked earlier. Okay? Okay, let's see, we got about, well, tell you what, because I still got this example to go over, move the camera, and then I want to go over this first part of the next software assignment before you do the second part. And we're at almost the top of the hour, so why don't we take a break till 5 past, and I think it will only take another 15 or 20 minutes to finish, and then you'll be able to, you know, work on whatever assignment you want to work on. Okay? So I'll start up again at 5 past.
Yeah. Oh, wait, we didn't like a lot of. Well, I don't
I
know.
know the block trade, but I like remember that. Yeah.
Just stop caring.
Like,
Yeah, I think it's a little bit.
I noticed that if you. Like some reason take like a 4-bit number, 7, obviously that's not like. Then it goes to 1, and then I think that. But I changed hot file. That it's like now 32-bit, and so that way it's above. Then it's just gonna. Okay, do you think that's fine?
Yeah, well, it. The multiply itself. Yeah, we do that. But it's fine to have it.
Yes. That was the thing, when I did select 6, it did go to the default, but then 7, it went back into the. Well, it's 3, but I was thinking, like, what if somehow orbit?
Well, are you?
Yeah, that's what it's there.
I'm using 3.
Well, the only thing, well, tested by itself, it's still deleted by itself.
Right.
Maybe that one, let's see, they separated, it's 3 of it, but you're not using all of them. So in your same page, you do like 0 and 9, like a.
No, I did.
Well, I mean, it's still doing stuff. If you test it by itself and it still doesn't, you know it's not. If you test it by itself and it's okay, So do that, but it made you buy and put.
So you're saying that these, the. Put into the market, the like, that 53 bit.
Yeah, that should be, that, because you got more than 4 selected. Yeah. Yeah, I'm just wondering if maybe. That's. But maybe it doesn't, it might depend on the version. What version?
No, I did everything, so.
Yeah, the key thing is though, and that will tell you a lot, and that will tell you. Something with a connection.
Was it trying to go with them? Oh, sure. Still the same. The other people being felt that people like walking up to the upstairs. I mean, like, right, it seems like.
There's good. Let's see. I can use it.
Yeah.
So we're actually. He's like, oh, and then he's like, second. They were saying that it was. Yeah. I couldn't hear. Yeah, it's like, so then I was like, oh. And he's like, I need to.
Okay, so it looks like it's 5 past, so let's go over this example of a case statement and assembly, and then I'll do the first part of software two. And you can do the second part after that, or work on your program counter if you need to finish that. So here's the flow chart, as you can see, and again, we're comparing contents of a register to a number, right, an immediate. If it's true, we're gonna do some stuff here, otherwise, we're gonna make this decision. True, do this stuff, otherwise, make this, or do this decision. True, do this, otherwise, we just do some other stuff. So it's set up like a case statement, right, like option one, option two, option three, default, basically. Okay, so just like in a previous example, you know, when you're gonna compare contents of a register to some number, you have to put that number in a register. So, you know, I just used the add-I again. And let's see, I used register 6. We already talked about register 0. Right, I'm just gonna add 5 to the contents of register 0, which is 0, which is gonna result in 5, and then that's gonna be in our register 6. And then we're gonna compare that to register 5. So that's a BEQ branch of equals. X5, X6, and then we put a label. I just used LBL1, the shorthand for label. And then, you know, down here someplace, put it right about here. We'll have our label, and then, you know, we just do whatever code we want to do for that option. Okay, so that's like the first part of the flow chart. Okay, then, you know, this is doing a comparison to 5, right? Because that's what we put into register 6. Now the next comparison, I want to be 10. So I can use another add-I. And we can just go ahead and add 5. Right, add 5 to what we already have in register 6, right? Because this add-I put 5 into register 6. So there's 5 here. So now if I just add another 5 and then put the result back into register 6, now I have 10 in register 6. Okay. One of the things, and the reason why I'm kind of speaking this out loud, I mean, one is because you're learning this and I want you to, you know, hear what I'm thinking. But even when you do it yourself or you're working with somebody, it's good to go exactly through that exercise, because usually, especially when you get, you know, into more lengthy type of assembly language programs, usually a common mistake is people lose track of what's in the contents of their registers. And they might think, you know, that there's a 0 in this register, or there's a certain number when there's something else that they didn't account for, and that throws everything off. So you just gotta be real careful. And that's where the simulator, the RAR simulator it's so nice, right? Because remember how you can look at the contents of the register as you step through your instruction. So, you know, that's how you can troubleshoot, right? If your program's not giving you the intended result, you can step through it and see, oh, are the registers, the contents of the register is what I expect it to be at this particular instruction. Because usually when there's a problem, that's what it is, you know, like, for whatever reason, you have, you know, something in a register that you weren't counting on. So anyway, that's gonna now put a 10 in our register 6. So now we can do another comparison. EQ 5 to 6. And we do the second label. So we have another label down here with the code for that option. And then what am I gonna have to put in between here? A jump, right? Right, we want to jump here because if we go to this option, we don't want to run into the other option, right? So we put a jump in, oops. Not Ed, and we'll jump to Ed. And down here somewhere, we'd have the trap. And the trap that we talked about earlier. Okay, and then, yeah, we got another decision point here, we're comparing to 15. So I would do another add I. Right, where now I'm gonna add 5 to 10. And now my contents of register 6 is gonna be a 15. And then I do another branch of equal. Have a label 3 down here. I mean, you know, if you have more options, right, it's just gonna be more of the same. But then you also need to have, you know, if it falls all the way through, right, it's none of these options. You effectively have to have a default. And just like in these examples where the false label was optional. Here, when you're doing a case statement like here, like this, you don't necessarily have to put the default. Okay, but again, it's good for readability, right? Because if it's none of these options, it's whatever the default's gonna be. And again, you'd have some code, whatever your default code is. Default code could just be jumping to the end. You know, it could be something. But you do eventually, you know, when you're done with the default, you want to jump over your other options. Okay? All right, so like I said, these are just, you know, some basic examples. Now we have a specific problem to do. And like I said, I'll do this one in class. This is the first part of software number 2, and then you'll do the second part of this as an assignment. So this first part, we're taking in a 32-bit unsigned from the switches. The switch addresses, hex 1100, all zeros, and that's always true. Okay, for this class, it's always gonna, the switches are always gonna have this address. Now, by the end of the quarter, like probably like the 8th week or so, you'll know how to change it. Okay, so, it's possible that when you do your, final project, it's possible for some reason you might wanna change this, and if you do, you'll be able to do it. But for everything we're doing up to that point, this is always the switch address. Okay, so if the input, so if the switch data, when I say input, I'm talking about the switch data. If that switch data is greater than or equal to this number, 32,768, we're gonna divide the input value by 4, okay, and ignore the remainder. Okay, if the input value is greater, or excuse me, if the input value is less than this 32,768, well, then we're gonna multiply the input value by 2. That's what I mean by this X here is multiply. Like we said, divide up there is multiplied in there. And then we just write the result to a 7-segment display. 7-segment display has this address. It's 1100 and then 0040. I think I mentioned this before, but let me say it again in case you've forgotten. This little underscore that I'm putting between the groups of 4 hexes, that's just for readability. Okay. You know, just because if you put 8 of them in a row, sometimes it's easy to miss one or add an extra. So that's the only reason for that little underscore. All right, so anytime you're doing a software problem in this class, what do you do first? Right, draw a flow chart. So let's do the flow chart for this. Remember, flow chart, you always start it with an oval with start or begin. And then what would we do next? What's the first thing we're gonna do? Yeah, you're gonna read the input, read the switch, okay? So what kind of shape is, when you're doing like anything with the input or an output? Yeah, parallel. These. So, switch data, whatever you want to call it. Input switch data. Then what do you suppose we would do next? Flow chart. Because once we've got the switch data, what do we want to do? Everywhere you see input, this thing switch data, right? Because the input is the data we're getting from the switches. Don't we want to make a decision based on what that data is, right? We want to do a comparison to this number to decide what we're going to do, right? So that's going to be what kind of shape in our flow chart. Right? That's the diamond shapes. So we're looking to see whether, let's see, how did I write in? Whether the input is greater than or equal to what's the number 32,768. Okay, and if it's true, we'll go this way. If it's false, we'll go this way. So if it's true, we want to do what? Divide by 4. Okay, anytime you're doing a process, right? Addition, subtraction, division, multiplication, and or, any kind of process, it's just a square or a rectangle. It can either be a square or a rectangle. Okay, so this would be divide by 4 if it's true. And then if it's not true, multiply by 2. All right, and then what would we do after that? What would this look like?
Right square, like LED.
Well, it would be right to 7-segment display, or yeah, we're using the 7-segment display this time instead of the LEDs. But remember, anytime, oops, I forgot an arrow here. If I forget something, please, whenever I make a mistake, please let me know. Yeah, I forgot to put an arrow. You gotta show the flow of the chart, right? So it's called a flow chart. So yeah, it's the 7-segment display, and then also remember, use a parallelogram for input and output. So you have a parallelogram here. Output 7-seg, oops. Done. Then these would come together, right? Because whether you're multiplying by 2 or dividing by 4, depending on this decision point, it all comes together, right? Because once you multiply by 2, you want to output it. Once you divide by 4, you want to output it. So it all comes together to the output of the 7-segment. And then you should always show where the flow chart ends. So you always show where it starts, always show where it ends. Okay, but that's what the flow chart would look like for this. Any questions on this? All right, so let's look at the code. Now, I don't know if I mentioned this during the first assignment, probably not, because the first assignment, the first software assignment where you had to basically take the 2's complement, there was only really 2 ways to do it, right? You could do it with inverting, then adding 1, basically 2 instructions. But some of you noticed that if you look through the instructions, there's actually an instruction called neg that basically does those 2 instructions for you. So you could either do it in 2 or 1 instruction. As the programs get more complicated, this one's a little bit more complicated, the one you have to do, and also this one at the board. There's more than one solution, okay? Just like most things, right? In this class, you're not graded on efficiency. So, don't worry about if you're doing this in the least amount of instructions, okay? Because you're not graded. Okay, you're just graded on if it works, okay? All right, so the way I did this, and again, this isn't the only solution, but the first thing is just like the first assignment, we've got to put the address of the switches into a register to then use it as an address in a load instruction. So that's where the li command comes in, the load immediate, just like you used before. I put it in register 5, just like I did before. And the address. Okay, so in Raj, you can't put the underscore, otherwise I'm sure you'll get an error. Okay, so this is just going to store switch address. Right. right? Just stores this number, that's the switch address in register 5. Okay, now, we want to load, okay, well, or we want to load the data at this address into a register. So since we're interested in 32 bits, what load command am I going to use? Remember, there's several load commands, right? There's load byte, there's load half word, there's load word. Load word, yeah. So it's just going to be load word. And I'm going to use register 6. Then do you remember what this notation means? Because usually this throws people off at first. Like, what does this mean again? The 0 and then in parentheses x5. Like, what's happening here?
Offset, it's 0.
Yeah, this 0 is an offset. So it's taking whatever number you put out here, it's taking that number, adding it to the contents of this register, which the previous instruction, we put in this 1, 1, all zeros, right? So obviously I add 0 to it, it's just going to keep it this number. And now we're using this as an address. See, this load immediate was just treating this like a number. This instruction is now treating this as an address. So now it's going to take the contents of that address, which is the switch data, and it puts it into register 6. So you see this instruction actually puts the switch data into register 6.
Or
Oh. I keep using double dash because I keep thinking Verilog. Yeah, this should be this. Thank you. It's a conf.
Does it matter if we use the unsigned load word description?
Good question, because we did say unsigned here, didn't we? Yeah, is there an unsigned? Oh, no, there wouldn't be for the word, right? Let's see. Yeah, we got load byte unsigned, load half word unsigned. Yeah, load word doesn't have an unsigned. And you see where the signed and the unsigned come in with load, and the reason why you need to know whether unsigned or signed is because it's gonna fill all 32 bits of the register. So if it's unsigned, it's gonna pad it with zeros. If it's signed, it's gonna sign extend. But if you're 32 bits, you don't do either. So that's why but that's a good question. Yeah. Yeah, the reason why there's not an unsigned load word is because it's already 32 bits. So you're not gonna add with zeros or you're not gonna sign extend like you would with the others. So yeah, that's a good point. I didn't really think about that until now. So thanks for asking. So, all right, so now we have the switch data in register 6. And we want to compare that switch data to a number. So what do you think we have to do with this number like we did in these previous examples here? Remember in these examples here when we had to do a comparison to a number?
Add the number to the register.
Yeah, you got to put the number in the register. Now, like I said before, here I used an add I, okay? I don't know, for whatever reason, when I did this problem, I used another load immediate, okay? Load immediate is a pseudo command, add I isn't, it's probably better to use add I, but again, you're not graded on efficiency. From an efficiency point of view, it's probably better to use add I, but again.
What's the other real command of load immediate? It's not just add I, right?
Are you asking what instructions load I is made out of?
Yeah.
All right, well, here we go.
I feel like there'd be like a little bit of difference between load immediate and.
Yeah, you're right. And the way you find out, and it's exactly what I have to do, because I don't have it memorized, is I look at the description and it says right here, it goes LI instruction writes an immediate value to the destination register RD. This is in a pseudo instruction is equivalent to the following: add I, RD, X0 immediate. But then also if the immediate value can, well, that's true if the immediate value can be represented with a 12-bit number. If not, it's a combination of two instructions, add I and this LUI. LUI stands for load upper immediate, which we haven't talked about yet. But the point you make, and it's a good one, is that, to find out when you have a pseudo instruction, to find out like why it's a pseudo, just look at the description, it will tell you.
I guess in this issue, both would work though.
Yes,
Okay.
yeah, it goes, like I said, over here, I couldn't use the Lodi. Yeah, so, yeah. All right, so what I did next here is I did a Lodi, and then I put that number into register 7. The 32,768. Okay, and then we're gonna do the comparison, so there is a branch greater than or equal to, and this is where the unsigned comes in, because you have a branch greater than or equal to signed, and then you also have a branch greater than or equal to unsigned. So because we're treating the switch data as unsigned, we want the one with the U. So I put D, E, E, U. And then we're comparing what's in register 6 to what's in register 7. And then we're gonna use a label. I use label BID 4, right? Because if it's true, right, if this comparison is true, we're gonna divide by 4. So it's good to use labels that are descriptive. Right, I mean, we've been doing just, these examples very generic, label, true, false. But like anything else, readability is a good thing, right? So I would use descriptive label. So if this is true, we're gonna divide, so we're gonna come down here somewhere. Put this label and come back to it in just a moment. But if it's false, okay, if it's false, we're gonna multiply by 2. So I'm gonna use a label MULT2. All right, so now, what did we say earlier in the class about multiplying and dividing by whole numbers powers of 2? Right. Exactly, right. It's shifting bits in the appropriate direction and then also bringing in zeros. Okay, so now let's go to our instruction manual. And let me get the projector up here. I'm gonna have to cover this up in a minute. Okay, so this is our handy assembler manual that's on Canvas. And let's see what we have for shifting bits. Okay, well, look, here's a SLL that stands for logical shift left. And if you read the instruction, well, actually, if you look at the form of the instruction, it's got an RD, right, destination register, got an RS1, source register 1, RS2, source register 2. Okay, and it tells you that this instruction, it left shifts the data in the source register RS1 by the number of times specified in register RS2, replaces the vacated bits by 0, that's important, we want that, then stores the result in destination RD. Okay, so if we were gonna use this instruction to, let's see, this is the shift left, so we would use this to do what? That's the multiply, right? So we would want to just move one place over. Well, what would we have to do first for this instruction in order to shift it one place over?
Make the second register.
Yeah, we'd have to load that register, right? That's gonna take an instruction, right? All right, but let's see, maybe there's another instruction that would be more convenient, right? It's just, instead of just using the first one I see, let's see if we see something else. Like, look, the next instruction is logical shift left immediate. And look, it's got the I there for immediate, but RD like before, RS1 like before, but it doesn't have an RS2. Instead, it has shift amount. And that's the immediate. So you see that SLI instruction, left shifts the data in the source register RS1 by the number of times specified by the 5-bit shift amount value. Replaces vacated bits by 0, then puts the result in RD. So this instruction is just like the other one, but I don't have to use another command to put data into a register, right? I can just use this as is. Right, I would just put shift amount, I just put a 1 there. Okay, so the reason I point this out to you is, you know, this is where knowing what instructions you have is helpful, right? Because if you just pick the first one you see, it may not be the best way to do something. So it's good to kind of look around and see, okay? While we're in this section of the assembly manual, let's look at some of the other commands we have here. There's a set if less than. There's a set if less than immediate. I mean, that's not shifting, but begins with an S. Set if less than immediate unsigned. Set if less than unsigned. Set if less than 0, set if not equal to 0. All right, here we get arithmetic shift right. Okay, we'll come back to that. There's also arithmetic shift right immediate. But look, just like there's a logical shift left, there's also a logical shift right, which we would want for what? To the right. Division. Yeah, left is multiplication, right is division. So that's essentially, other than it being the opposite direction, it's the same type of command as SLL, right? The shift left logical, where you have to put the number in the register first. Well, look, there's an SRLI. Okay, so this would be the opposite of the SLI we just talked about. Okay, now go back. And let's go back to the shift arithmetics here. Because why are some logical and why are some arithmetic? Like, let's look at this one here. This FRAI. This is arithmetic shift right immediate. Okay, so let's read what it does. The SRAI instruction right shifts the data in the source register by RS by the number of times specified by the 5-bit shift amount. Well, that sounds a lot like the logic one, right? Okay, but here's the big difference. Replaces the vacated bits by a copy of the leftmost bit considered to be the signed bit. What's the significance of that? Why would we want to keep the signed bit the same?
Make sure the new number is the same sign, you can think to the right, so that this facing the left.
Exactly, exactly. Right, so you see, if you're dealing with sign, right, you want to maintain the sign, you want these commands, the arithmetic shifts. Okay? And you'll notice there's no shift left arithmetic, right? There's shift right arithmetic immediate and there's shift right arithmetic, which is the one where you got to put the number in the register. Oops. Okay. But there's no like shift left arithmetic, no shift left arithmetic immediate. And why is that? You actually implied it, but why wouldn't you have a shift left arithmetic? Why is it only shift right arithmetic? Yeah, we changed the number because the sign bit is the most significant bit, so it only matters when you're going right? You're not going to ever do arithmetic shifting the other direction because the least significant bit is not your sign bit. So you would change the value. Okay. All right, so let's go back to the problem because for this problem here, we're just going to use either a shift logical left immediate or a shift right logical immediate. Okay. Okay, so we'll do with my program here. So let's look at the multiply first. So what I did is I used that shift. Logical left immediate. And let's see. Our number is in register 6. So we're just gonna take our input value, shift it left one place, and then put the result right back into register 6, right? So our shifted, our multiply by 2 is gonna be in register 6 when we're done with this instruction. And then we would just go to the end. And the end is gonna be down here somewhere. Right, because at that point, we're done multiplying, so we would want to output at that point. Okay, so that's if our value is less than this 32,768. If it's greater than or equal to, we're going to divide by 4. So this is going to be a shift right. And I'm sorry, well, let me fix this. Let me line it up a little bit better. Okay, 4. Okay, just for. So if we're dividing, it's gonna be a shift right. Load immediate. Again, register 6, but here we would shift 2 places, right? Since it's a divide by 4. So, here is multiply by 2. Here is divide by 4. Oops. Divide by 2. All right, yeah, so if we're done dividing, then we're just gonna do the same thing, right? We're gonna go ahead, and the way we end it is we're just gonna write to the 7-segment display. So this is where, again, having an offset is handy, right? Because we haven't done anything to the contents of register 5 since we put in that switch address, so it's still there. So now when I write out to my 7-segment displays, right? When I write my result, whether it's the multiplication result or whether it's the division result, it's gonna be a store word. And I'm taking our result that's in register 6. And I'm gonna put an offset of 40 to the contents of register 5. And that's gonna output to the 7-segment display. It would be output to 7-seg. Right, so again, what this is doing, it's taking that switch address that's in register 5, it's adding 40 hex to it. That now makes it the address of the 7-segment display. And then the data, our result that's in register 6 is gonna go to that address. It's gonna be written to the 7-segment display. So see, that's why this instruction was created the way it was with the offset, is because once you have an address in there, now to change it to some other device, all you're doing is using the offset. If you didn't have this offset feature, you would have to do another load immediate into a register and basically, do this over again. Right, so, I point that out because usually if I don't point it out, people ask that. They're like, well, why have this offset? It seems to make it more complicated. Well, it's actually a convenience. Okay? All right, so now, again, I want to point out, this isn't the only way to do this. Okay, there's other solutions. Okay, and when you do part 2 of this assignment, there's going to be multiple solutions. So, and again, you're not graded on how efficient it is. So, don't think there's only like one way to do it. All right, so do you have any questions? Because that's all that I wanted to cover today. Like I mentioned at the beginning, your priority should be getting your program counter to work because that's due tomorrow. But if you have your program counter working, you can work on this. This is due this Friday. Okay, so do you have any questions before you get started with your assignments? All right, if you have questions, please let me know.